We're back. Now we're starting Unit 5, which was discrete and continuous distributions. I'll start with a review of discrete distributions. Remember, a discrete variable is a count of some random variable. There are multiple types. A generic discrete distribution gives probabilities associated with each possible x value, or requires you to calculate those probabilities yourself using Unit 4 rules. This is typically displayed as a table or a histogram, but it doesn't have to be. So let X be the number of courses for which a randomly selected student at a certain university is registered. So notice it goes from 1 to 7, but they skipped 4. Oh no. First of all, notice it doesn't start at 0 here. The reason it doesn't start at 0 is because you can't be registered for 0 courses and still be a university student. So these X's can be any number. They do not have to start at 0. So what are we going to do to figure out 4? Well, first of all, remember all probabilities have to add up to 1. So if these are all the possible outcomes, they all have to add up to 1. So to figure out X equals 4, I'll add up the other 6 numbers and then subtract that number from 1. When you do that, you get 0.25. So it's adding up all of the probabilities besides 4 and then subtracting from 1. Probability X is less than 4. It's going to be these 3 numbers. So you add those together, you get 0.14. The probability X is less than or equal to 4 would now include 4. So it's going to include all 4 of these numbers. So this, and also the 0.25, which is 0.39. What is the probability the student is registered for at least 5 courses? So I want the probability X is greater than or equal to 5. So it's going to be everything greater than or equal to 5. So 0.4 plus 0.16 plus 0.05. What is the mean and standard deviation of this distribution? So to do this, I want the mean and standard deviation. The mean is the one you're much more likely to need on the AP test. It's X. You take each X times the probability and you add them together. So I do 1 times 0.02 plus 2 times 0.03 plus 3 times 0.09 plus 4 times 0.25 plus 5 times 0.4 plus 6 times 0.16 plus 7 times 0.05. When you do that, you get 4.66 classes. This is the formula for standard deviation. But remember, what you should do instead is type your X's into list 1. Type your probabilities into list 2. Then you go to 1var stats. Your list is going to be L1. Your frequency, that's how often it happens, which are probabilities, is going to be L2. When you type that in, you should be able to check your mean, but you would still need to show work on your mean. So you can get your answer that way, but you have to show work when you do free response, which is the only type of question you'll be doing this year on the test. So you have to show work, so you can check your answer that way, but still show your work the way I just told you. And then you should get your standard deviation as well when you do this. The next type of discrete distribution is a binomial distribution. This is where you have a set number of trials and probability of success remains constant. To show work on the free response, we write it this way. We write out our distribution, and then we have our probability statement equals the answer. So we're going to be looking for 3 things on the work. The description of your distribution, your probability statement, and your answer. Remember, n is the number of trials, p is our probability of success. We use binom PDF for equal to. We use CDF for less than or equal to. If we want greater than or equal to, we need to manipulate the numbers to turn it into a less than or equal to question. And these are the formulas for our mean and standard deviation. These are on the formula chart. Remember, mean is also called the expected value. And this is true for all types of distributions. In a certain county, 30% of voters are Republican. How many Republicans would you expect? So they're asking me for the expected count out of 10 randomly selected voters. So I just do n times p. So n, I have 10 Republicans. I expect 30% of them. I have 10 people. I expect 30% of them to be Republican. So I expect 3 Republicans. For a mean like this, don't round to a whole number. I know this one already is, but for future reference. Now, if it said, what is the minimum number of Republicans I need to select in order to expect at least 30%, assuming that this was like 2.9, then I would have to do 3. But since it's just how many would you expect, that means how many would you expect on average. For the standard deviation, you do the square root of n times p times 1 minus p, like so. Don't forget units on both of those. What is the probability that no more than 6 will be Republican? So this is where you use your calculator. No more than 6 means less than or equal to 6. So I'm going to describe my distribution. So I do b parentheses n, which is 10, comma 0.3 chance of success. And then I do the probability x is less than or equal to 6, which is what the calculator already does, so I don't need to manipulate anything. So remember, I'm using binomial CDF for this. That's not part of my work, but that's what I'm using. Which you get by going to second vars. And it's actually near the bottom, so you should go down. What is the probability at least 7 are not Republican? So now we're looking at the ones who are not Republican. So we have a 70% chance of getting a non-Republican in this county or town, whatever it is, county. So I still have 10 chances, or I still have 10 chances. But now I'm looking for non-Republicans, so I have a 70% chance of success. I want at least 7, so that means x is greater than or equal to 7. So the way this works, these are all of the possible numbers of successes that I could get when I have 10 trials. I want at least 7 successes. So I want 7 or more. So I want one of these. But I can't do 7 or more. I can only do less than or equal to. So instead of doing 7 or more, I'll do the opposite of what I want. The opposite of what I want is from 0 to 6, like this. So instead of doing greater than or equal to 7, I'm going to do 1 minus the opposite of that, which is the probability x is less than or equal to 6. We only have to do this for discrete variables. We never have to do this for continuous variables, where we like go down a number like that. So when you type that in, you should get 0.6496. The next type of discrete distribution is a geometric distribution. For a geometric distribution, probability of success again has to stay the same for each trial. But for this one, you continue until you get a success. So you're going to keep going until you get whatever success that you want. So for example, say you really want a girl, you're going to keep having kids until you have a girl. And that would be your success, and then you would stop. Not the best life plan, but go ahead. To show work, unfortunately, there's not a nice pretty shorthand. So instead, I just write out geometric and then p equals whatever that number is. And then again, so that's describing my distribution. And then I have my probability statement equals my answer. So if I look for your work, I'm looking for this, this, and this. Or do the actual calculations. We use geometric PDF again for equal to. CDF is for less than or equal to. Here are the mean and standard deviation, which are on the formula chart. Thought I would fix this. I believe the way it is on your formula chart this year is the square root of 1 minus p over p. That's the same thing as just taking the square root on top and bottom, and then you're taking the square root of p squared, which is just p. So I believe it's written in that form, but obviously both formats gave you the correct answer. What is the probability the first 3 rolled is on the 4th roll? So you're saying your first success is on the 4th trial. So this would be geometric. Our chance of success is 1 out of 6, like that. So there's my distribution, there's my first check. I want it to be on the 4th roll, so I want the probability x equals 4, there's my statement, equals my answer. So I would have used geometric PDF to solve this. Or, so this would get you full credit. This would also get you full credit. If I want my first 3 to be on the 4th roll, that means the first 3 rolls were not 3s. So I had a 5/6 chance of getting a not 3, and I wanted to do that 3 times, times the probability I get my first success on the 4th roll, which is 1 out of 6. So in this case, this gets me the same amount of credit as this. So that counts as both of those things. And then I have my answer, so I'd get full points here. What is the probability the first 3 rolled is at least the 4th roll? So that means, again, it's geometric, p equals 1 out of 6. But now I want x to be greater than or equal to 4. So that's 4, 5, 6, all the way to infinity. Instead of doing that, I'm going to do 1 minus the probability x is less than or equal to 3, because that's what my calculator can handle. It can't handle greater than or equal to. Don't know why. It seems like an easy fix. But they didn't ask me. All they have given to you is less than or equal to. So that's 0.5787 when you type that in. Alternatively, your first 3 rolled is at least the 4th roll. That means your first 3 rolls have to be 3s. After that, you don't care what happens because you don't care when you get your 3. All you care about is that the first 3 rolls are not 3s. So you could also just do 5, 6 to the 3rd power. So either of these would get you full credit. The next type is a continuous distribution. So numerical variables whose values fall within a range or interval. These are going to be from measurements. They can be described by a density curve like this one. This is obviously a triangle. So this is like the unusual problems we talked about. It's terrible. It's fine. These are usually not on the AP exam. I mean, where they give you a shape and have you find the area. Not typically on the test. Probably not going to be on the test this year. But if it is, all you're doing is finding the area. So when I say x is greater than or equal to 1, that's a trapezoid. I'm trying to find the area of that trapezoid. So this height right here is 0.5, or base if you prefer. This base 1, so this is at 2 right here. So 1 is going to be halfway between here and here. So that means the height at 1 is going to be halfway between here and here. So it's halfway between 0 and 0.25, which is 0.125. So I use my trapezoid formula, which is 1/2 base 1 plus base 2 times the height. The height is this distance right here. Or between 1 and 3. So it's a smaller trapezoid. I need a new height here, which is halfway between 0.25 and 0.5. So this is 0.375. Because 0.25 is at 2, 0.5 is at 4, 3 is halfway between those, so I go halfway between those heights. So good to know. Remember, the whole area adds up to 1. That might come in handy, but probably not on the test. Uniform are also typically not on the AP exam, but they are fair game, so they could show up. This is a continuous distribution that is evenly or uniformly distributed. Probabilities are calculated by finding the area under the curve, which is obviously going to be base times height because this is a rectangle. To find the mean, it's just the average, so it's the middle of the rectangle. Standard deviation is b minus a over the square root of 12. These are not on charts, but you probably won't need them. And then for your height, remember the area of this rectangle is 1. So if you know the base of the rectangle, area equals base times height, the area is 1, and you know the base, so it's going to be 1 over the base is going to give you the height. So evenly, that means uniformly distributed with a minimum of 5 and a range of 35. So that means the difference from the minimum to the maximum is 35. So if the min is 5, I must make the max 40. And then to find my height, it's 1 over the base, which I can get by using this process. What's the probability? It takes less than 20 minutes. So 20 minutes, about here. Less than 20 means we're going from 5 to 20, so the length of that base is 15. Times my height, which is 1 over 35, which is 0.4286. The next type of symmetrical, or the next type of continuous distribution is a normal distribution. This one is usually on the exam. I would say always on the exam, but we don't know exactly what will happen this year in 2020. So it's a symmetrical bell-shaped curve like so. To show work on free response, this is how we describe our distribution. And then again, we need our probability statement equals our answer. We use normal CDF, never PDF. And we use inverse norm if we're trying to find X or Z. The lifetime of a certain type of battery is normally distributed with a mean of 200 and a standard deviation of 15. So we write our statement, or we describe our distribution like that. So that would be the first check. What proportion of these batteries can be expected to last less than 220 hours? So here's my probability statement. That's what I'm trying to figure out. I'm going to use normal CDF to figure this out. So the mean is in the middle. We're at 220. We're shading less than that. So I can see that I'm shading well over half. So this part is not part of your work, but you're going to use normal CDF. You have your lower bound over here, somewhere is going to be negative infinity. Your upper bound is the 220. You type in your mean and standard deviation, you get 0.9088. So when your person is grading this, they're looking for your distribution. Your probability statement equals your answer. That's not part of the work. I'm just showing you so that you can see it later. The lifetime of a certain type of battery is normally distributed, blah, blah, blah. How long must the battery last to be in the top 5%? So now I'm telling you the area is 0.05, and I want to know what X value is right there to make the area above it 0.05. So I'm trying to do the opposite. Now, instead of knowing what the number is, I know what the area is, and I want to work backwards, or I want to do the inverse. So again, there's my probability statement. My distribution. My probability statement, I'm going to say the probability X is greater than K. So I'm trying to figure out what this number is, and I'm going to call it K. Could also call it X1 if you want. Is 0.05. So 0.05 is my area, and this is the area to the right. When you do inverse norm, if you have a fancy new calculator, you can tell it you want the area to the right. If you have an old calculator, you have to do the area to the left. And the area to the left here is 0.95. So if you do the area to the left, which you have to do if you have an older calculator, you type in 0.95. If you have a new calculator, you can either type in 0.95 and do to the left, or you can type in 0.05 and do to the right. When you type that in, you should get 224.6728 hours. Please make sure you're typing in these examples because you need to make sure that you know where everything is located. So remember, I'm looking for this, looking for this, I'm looking for that. I don't care about the calculator notation. Now here is our sprinkle of Unit 6, sampling distribution. So we talked about this on the first and maybe the second day of the unit for 6. You did a homework assignment over it, but then you didn't practice a whole bunch. Sampling, so we're going to review this now. It really falls in with the probability, but we didn't put it in Unit 5 because we already had too many things in Unit 5. A sampling distribution is the distribution of all possible values of the same size in the same population. Sometimes we're taking a sample of n items. When we calculate probability, we need to use the modified mean and standard deviation, which we'll look at on the next slide. Then we solve using normal CDF or inverse norm as long as normality applies. For proportions, for normality to apply, n times p and n times 1 minus p have to be greater than or equal to 10. For means, it needs to be given in the question, or n has to be greater than 30. Remember, the central limit theorem tells us that if the sample size is at least 30, the sampling distribution is approximately normal, even if the original population was not normal. If the original population is normal, though, all sampling distributions are normal. So if we're doing proportions, then the mean of the p-hats is just going to equal the population proportion. So the means are pretty easy. And the standard deviation is going to be this thing. If we're comparing two populations, then we subtract p1 minus p2, and we use this big ugly thing. Well, it's not that ugly. We use this formula for standard deviation. For one population, the mu of x bar is equal to the mu. Sigma of x bar is equal to sigma over the square root of n. So sigma of x bar means the sampling distribution. Oh, it even says sampling distribution here. And then that's what we do if we're comparing two means. Remember, you get this formula chart on the test. For this year, 2020, you'll have to print it out and have it ahead of time. Or remember, I gave you a copy, so you should have a copy already in your folder. You might be able to access it during the test, but it will be easier if you have it printed out ahead of time. Maybe we'll be back in school and I can print it out for you. Maybe. Assume that 30% of the students at AHS were contacts. In a random sample of 100 students, what is the probability that more than 35% of them were contacts? So I'm trying to find, I'm using a sampling distribution, I'm dealing with proportions. First, I want to make sure that normality applies. So for normality, I check n times p. Remember, p is the population proportion. It says assume 30% of students at AHS were contacts. So this is p. This number over here is p hat. Oh, this should say equals 70 before I do the greater than or equal to 10. N is 0.3, or n is, we're doing normal distribution. Parentheses, our mean is going to be equal to the population proportion. Our standard deviation is going to be the square root of p times 1 minus p over n. And then we have p, we want the probability that p hat is greater than 0.35. So that's going to be my lower bound. E99 is going to be my upper bound. This is going to be my mean and my standard deviation. And when you type that in, you should get 0.1376. The Army reports the distribution of head circumferences among soldiers is approximately normal. So they're telling us it's normal, with the mean of 22.8 and a standard deviation of 1.1. I don't know why they know that, but they do. What is the probability a random sample of 5 soldiers we'll have an average head circumference that is greater than 23.5. So we're not just looking at what percent of soldiers have a head circumference above 23.5. Now we're looking at a sampling distribution. We're saying if we take a sample of 5 soldiers, what is the probability that the average circumference is greater than 23.5? So this is a sampling distribution. So it's normal because it was given in the question. If it wasn't given in the question, then our sample size would have to be 30 or higher. Or if a different shape was given in the question, if it was 30 or higher, the sampling distribution would be approximately normal. We do our mean, 22.8, and then our standard deviation is going to, of x bar, is going to be sigma over the square root of n. And this is the one we use more often. You might see the proportion, or you might see 2 means or 2 proportions, but this one comes up a lot more often. So this is sigma over the square root of n. And then we have the probability of x bar is greater than, I'll write it over here. So I want the probability that my sample mean is greater than 23.5. So again, that will be my lower bound. E99 will be my upper bound. And when you type that in, you should get 0.0774. What average head circumference for 5 soldiers would be at the 30th percentile? So remember, percentile is the percent below. So I'm saying I want 30% below, and I want to know what x bar needs to be there. So I'm using the same sampling distribution as above. I want the probability that x bar is less than k is going to be equal to 0.3. So I use inverse norm. This time your area is already the area to the left. Remember, if you're using an old calculator, your area always has to be to the left. If you're using a new calculator, you get to pick. But obviously you should pick to the left here, and you shouldn't change it. When you type it in, you get 22.5420 inches. So x bar is going to be less than 22.5420 inches to be at the 30th percentile. Or at the 30th percentile would be actually 22.5420 inches. It's the end of probability review. Email your teacher or come to office hours if you have any questions. Good luck on your FRQs.